and welcome to our next VELOVirtual session. Today, we're going to be looking at the future of static mixers. So in a way, this is also a proxy for the future of any critical application manufacturing. But static mixers are another example of where you can take solutions like Ansys, Velo3D, and then unlock capabilities to fully optimize a design. And that's really the critical direction here. In this cycle of design, simulate, manufacture, test, the comments that we tend to hear a lot from our customers is you might be able to design it. You can definitely simulate it with powerful software like our partners at Ansys are bringing to the table. But our customers were struggling to manufacture it until they found Velo3D. And so, and I don't mean that they couldn't make a prototype or project work. I mean full production, right? With redundant, standardized, distributed supply chain. And that's really the value that we're going to be bringing to the market and talking about today. If you kind of bring it back to static mixers, lots of engineers in many industries are using static mixers to combine, condition, or mix fluids, and they feature a lot of advantages. So energy savings, that's a key initiative in a lot of markets today. Mostly maintenance free, which is nice, no moving parts. And then they tend to be really cost effective for what they do. But as a designer, you've got to balance here. You've got to face a challenge of balancing the ability to mix a fluid with the need to keep the fluid moving. And getting that balance is key. And for that, you need a flexible manufacturing solution. So, whether you're looking high ambitions to maybe colonize a new planet or just make the most of the one that we're living on today, the power of advanced simulation from Ansys, the power of advanced manufacturing from Velo3D, it's proving unparalleled at solving the most complex engineering challenges for higher performing metal parts. And this is a story that we're seeing a lot of today. Now, let me introduce our speakers. It's an honor today to introduce Ethan Thompson. So Ethan is a senior application engineer at Ansys, specializing in upfront simulation technology like Ansys Discovery. Prior to Ansys, Ethan spent time as a design engineer in the industrial equipment sector, leveraging Ansys products, where he performed hyperelastic structural analyses for vibration isolation systems. Say that 5 times fast. Ethan holds a bachelor degree in aerospace engineering from Penn State. And when not helping customers be successful with Ansys products, you can find him on the golf course, tinkering with automobiles, spending time with his family. So welcome, Ethan. And Ben Wilson. Ben is an applications engineer at Velo3D, helping customers realize their innovations with Velo3D's support-free metal AM solution. Prior to joining Velo3D, Ben worked for 5 years in the Metal AM group in both R&D and production sites at Honeywell Aerospace. Ben has a BS in mechanical engineering with a focus in jet and rocket propulsion from Embry-Riddle Aeronautical University. So we got 2 rocket scientists joining us today, but I want to turn it over, Ethan, to you.
All right, thanks for the great introduction there, Mike. So hello, everyone. My name is Ethan Thompson. So as Mike mentioned, I'm the application engineer here today, going to be talking about our Ansys Discovery product. So for those of you who may not be familiar with Ansys, I'm going to start at a super high level. Ansys is a physics simulation company that helps aid in the product development process. We have a multitude of different products that address several different physics. So depending on your application, we have a variety of different products that might fit your product. So today, we're going to be focusing on our Ansys Discovery product, which is one of our newer products here today. So if we think about the current state of simulation, there's often a few select engineers that are going to be your simulation experts at your company. They often sit up in this ivory tower, and design engineers, outnumbering these simulation experts, often, almost an order of magnitude difference between them, 10 to 1 is kind of what we see. Is that, every time a design engineer needs to go ahead and explore their design, they need a way to validate. And these are the simulation experts that help validate these designs. Now, with the difference between the numbers of design engineers to these simulation experts, there's a lead lag where you're going to see a bit of a delay coming back from results from these simulation experts, just due to the level of complexity and the level of inquiries that they get on a daily basis. So what we're trying to do here with Discovery is try and bring simulation to the forefront of the design process. Typically we see simulation used in the detailed design phase where you're really trying to shake out any last minute features or trying to validate performance. But in the conceptual and the preliminary design phases, where you're really in that malleable stage where you're squeezing Jello, trying to understand what are the best processes for your design, simulation really isn't being used today. So we at Ansys recognized this and brought in Ansys Discovery to go ahead and kind of address some of these needs. So how it can be used is primarily in two different ways. So the first one is a design engineer. And so how we are going to do this is we've really created an immersive experience that's very easy to use. And so this tool allows engineers who don't live in simulation on a daily basis to go ahead and enter this environment and rapidly explore their designs with physics in the background. Now, the secondary way is, maybe you don't want to go ahead and expose your design engineers to simulation. It might be a little bit too much for their plate. So what we've done here in this Discovery product is combine a multitude of different physics solvers and physics complexity. And what we can do is help speed up your current expert simulation workflow today. So to address how we're doing this, I want to highlight some of the key capabilities of our tool. And the three primary capabilities can be seen here on the left side. And so these actually mirror the different modes that we have within our tool. So at the foundation of every engineering design is going to be our CAD. So what we've done here is we've introduced our space claim technology, which is a CAD agnostic direct modeling technology, meaning that we can bring in CAD formats from any format. We're talking neutral, such as STEP or STL, or native, such as geometries from Creo, NX, SolidWorks, or the like. So what you're able to do in this environment that has physics in the background is quickly manipulate and modify your designs using the direct modeling technology. So for those of you who might not be familiar with direct modeling, think of it as a way to just simply grab an object and move it around. You're not tied to the original parametric tree. So geometry is our foundation, but we have two different physics solvers here, which are going to be our live physics simulation, which is in our explore mode, and we have high fidelity simulation, which is in our refine mode. The live physics simulation is great for design exploration. That's why we call it our explore mode. And what it's going to be able to do is give you simulation results orders of magnitude faster than you would in any other product. So think about if you're able to look at a baffle duct like this, you're able to move around these ribs or these veins and quickly see the redistribution of the flow without waiting, minutes, hours, or even days in some complex scenarios. So with all these different capabilities, we wanted to go ahead and have the ability to transfer these to these flagship tools at Ansys, just so we can continue to keep that digital thread during your design process. So today's focus here is static mixers. So I'm sure most people are familiar. So it's like Mike mentioned, it's a motionless mixing device. There's a variety of different design types that you can go ahead and explore. There's a variety of different design considerations here. We have a sample one that we're going to be utilizing today here on the right. But some of the things that you're going to be considering is, what type of vane do I want to use? How many and what are the orientation? And as you're exploring this, there's definitely a lot of different considerations you need to look at on the background with respect to performance. Specifically, these are going to be relating to pressure drop and trying to have a homogeneous flow at the end. You want to make sure that, whether you're mixing two different fluids or two different temperature fluids, make sure that they come out at the other side completely mixed and uniform. So with that being said, let's go ahead and dive on into an end product demonstration here. What we are looking at right now is our explore mode in our Discovery software. And so what we have here is our static mixer. And just for the sake of demonstration here, I'm just going to go ahead and chop this in half so we can go ahead and take a look at what's going on in the inside. We have flow coming in through our main channel, and we have a secondary channel coming down through the top. And so for this application, this is going to be a mixing of two different temperature flows. And you can see here, we have a outside sleeve here as well that could be used for liquid cooling. But for this one, let's just focus on the design of our internal mixing components. So let's go ahead and begin to set up our simulation so we can begin to explore this design. As you notice up here on the top, we have access to all of our controls up here in the ribbon. We have the opportunity to explore a multitude of different physics within this platform. So depending on what you're looking for in your design, and this application, we are going to have a variety of different physics boundary conditions that might be applicable for you. So in this case, let's go ahead and begin to set up a CFD study. Now, often CFD is considered one of those, dark arts that everyone is a little bit scared of. But here in Discovery, we've tried to make this a very simple process. So what I want to do here is just focus on the main components of our flow here. And as you can see, I have my external sleeve with two different vane designs. So let's go ahead and consider our first vane design here. And for us to set up our simulation, we need to go ahead and create a fluid volume. And so what this is basically doing is just signifying where the fluid can go within this application. So let's just use one of our nice CAD tools here. In this case, it's a volume extraction tool. And what it does is it allows you to go ahead and generate the fluid volume for where the flow can go in your design. So as you can see, it basically just goes ahead and propagates through the entire design here so that you can quickly and rapidly go ahead and make things fit to the physical surroundings around them. So once we've done that, that's all the prep that we need here in Discovery. We've tried to make things very, very simple. So let's go ahead and apply some physics boundary conditions here. So on the front end, let's go ahead and apply our first condition here. And so in this case, it's just a simple flow condition. So I can do this up on my ribbon, which is access to a lot of my tools, similar to what a lot of design engineers are coming from a, like a native CAD tool. But we also have this hex and heads up display that allows you to go ahead and quickly apply boundary conditions. So in this case, let's just go ahead and apply a flow velocity of 1 meter per second. And let's get a thermal mixing component to this simulation. And let's turn on our thermometer here. And let's just assume that we're working with a room temperature flow. So this is just our initial component here. Now the second side, let's go ahead and add in a secondary flow here. So as you can see on the right side of this heads up display, there's definitely a couple different layers of abstraction in which you can do to apply different conditions. So make sure, depending on your application, that you apply the right condition. But for today's demonstration, let's just go ahead and work with our flow velocity. Now, once I added that 4 meter per second flow at the top, I can update my flow velocity temperature profile. In this case, I want to have a 60-degree temperature come down through the center and mix through these veins. So once I have my two inlets, the last thing I need to do here is set up my outlet. So here we just need to signify where the flow can go and simply change our inlet type to outlet. We can click this check mark. So just within a few clicks there, I know it's a little bit long-winded in terms of the setup, we have a fully defined computational fluid dynamics problem set up. Very quick, very easy here. And so the value here is that when you're going ahead and exploring a lot of these different designs, you're not burdened with the traditional tasks of simulation. We're trying to separate a lot of those, mundane and monotonous tasks that are bottling up the current engineering design process. So let's just go ahead and begin to solve this application so we can see some cool images here. So the one thing I want to note here in Discovery is that we both have a steady state and a transient fluid solver. And so what this allows you to do is go ahead and look at the application's long-term performance or from a time-sensitive manner. So what we're looking at here is the iterations of our steady state solver, or how the solver is going to its final iteration. And what we're looking at are our streamlines, which are showing the directionality of our flow, and they're colored with respect to the velocity of the fluid in that area. The one thing I forgot to mention is that we're assuming water for this application at this time. So let's go ahead and take a look at some of our other advanced post-processing so we can begin to understand how this design is going to be functioning. So as I mentioned, this is a steady state solver, so it's important to let this converge. But as you get a little bit more experienced with simulation, specifically CFD, you can glean some information from the early design iterations that you're seeing here. So right now we're taking a look at our velocity. You can see we're getting some areas of low and high flow velocity as we go through these veins. And so what we're seeing is effectively the flow velocity is going to slow down as it begins to mix. And what we're going to see here is effectively a pressure drop through our system. So here in Discovery, we have an opportunity to go ahead and not only look at some really cool results from a rendering perspective, we can also get some very specific quantitative results. So as you can see up here in the top right, we have a few monitors here that are populated. And so these are just some basic ones that we have applied with respect to the physics that is being solved, in this case, a thermal fluid simulation. Now, if I want to go ahead and look at some of our performance parameters that we wanted to go ahead, we talked about at the beginning, we talked about pressure drop, but we also talked about, making sure we get a really nice homogeneous flow at the outlet. And so one of the ways that I like to approach this from a simulation perspective, specifically on this design here with respect to static mixers, is that I like to go ahead and create some monitors. And so what I like to do here is to understand how uniform the flow is. I'll go ahead and set up a temperature at our outlet. And what I want to do is I want to set up one with respect to my average, one with respect to my max, and also one with respect to my minimum. And so you'll notice that these don't have any values yet because we're still solving our physics simulation. But ultimately, what these are going to do is basically tell you how aligned the results are with respect to a uniform flow. So for instance, you can see here that our max and mins are not too far off from our mean or our average temperature, signifying to me as a designer, hey, this is a pretty good assumption that our flow is being mixed very well. But no, we are only focusing on, just looking at some of the simulation components, not really the design side. So let's go ahead and flip over to there. So one of the great features of Discovery is the ability to rapidly iterate on your design with interactive CAD. So what we can do here in this design, if I would like, is maybe I'm seeing a really nice amount of mixing on this design, but maybe it seems like I'm getting too high of a pressure drop. What I can simply do is go up to my collection of vanes, identify any of my individual components, and simply delete. And what this is going to do to my design here is it's automatically going to reconfigure my volume extraction. You can see that it deleted the areas where the flow couldn't go, and we're already beginning to solve our physics simulation again. So keep in mind that as you rapidly iterate through your design, there's a wide variety of knobs that you can twist with respect to your design. And it's very valuable to have instantaneous or near instantaneous feedback from a physics perspective, because it's going to give you discrete feedback. You're not relying on tribal knowledge or best practices. This is a very direct way for you to continue digital threads for your design teams, but it also, as a design engineer, is giving you the exact feedback that you need with numerics behind it. So let's go ahead and maybe consider a few different design iterations at this point. So if we go ahead and take a look up here at our ribbon, we're working, or excuse me, with our geometry tree, we're working with our original vane design. So if I go ahead and orient this design here, let's rotate it 90 degrees, you'll notice that these vanes are very typical of something that you would expect from a part that is going to be additively manufactured. When we take a look at these vanes, we have some features here that are obeying some, we'll say, general best practices. In this case, I have a 45-degree angle, which is a general guideline for a lot of additive manufacturing, just to say, you really don't need supports at this angle. Now, however, you were partnered with our friends here at VELO today. So what I want to explore is my secondary set of vane options. And so you'll notice as I turn on these vanes, and I can simply go to my volume here and then update in the context, meaning it's going to update with what bodies are showing. You'll notice here, just as it quickly updates, these angles are much more shallow. So what this allows you to do here is quickly understand what the effects are with respect to different designs. So as you can see, we have a multitude of different designs here. We can go ahead and turn this back on, and we're already beginning to see some different results here. Now, the one piece that I really haven't talked about today is the secondary piece of Ansys Discovery. And I just want to highlight this really quick to make sure I can save some time for my friends at VELO. So this Explore mode is really great from a design exploration standpoint, hence its name. But oftentimes there are situations where engineers really want to go ahead and ramp up the complexity of their design. They want to twist those physics knobs, get really into the nitty-gritty details of advanced physics simulation. And that's what we can go ahead and do here today in our refine mode. So this refine mode utilizes the flagship solvers of Ansys simulation technology. So if we're running a fluid flow simulation, this will use Ansys Fluent underneath the hood, or if we're running structural or thermal, it's going to use our Ansys mechanical solver. And the one thing you'll notice here is that all of my physics conditions will transfer over. Everything is set up. The whole mode, or the whole tool, regardless of mode, is going to be in synergy with one another. So the last piece I want to go ahead and talk about really quick, we're going to hop back to my slides here, was the issue relating to the shallow angle of these vanes. And if we orient them again, just to highlight what we're looking at, these are about at a 20-degree angle off of horizontal, which from an additive manufacturing standpoint, basically signifies, hey, you would want to put supports in this area. And if we didn't, that would be a big no-no. So in this case, when we go ahead and see that we have these whole group of mixing vanes, it would honestly be a bit of a nightmare to try and remove some support material in these areas. So let's go ahead and hop back to my PowerPoint really quickly. So here at Ansys, we focused on our presentation here at Discovery, but we do have some solutions in the additive perspective that may be valuable for our attendees here today. So within Ansys, we have physics simulation for the design of products, but also from the manufacturing perspective. So one of our tools here is our Ansys additive suite. So we have our prep as well as our print side. So what prep can do is give you guidance on your build strategy with respect to orientation. It can give you feedback with respect to build time, distortion tendency, so that you can quickly align your geometry in the most efficient way possible. So if we go ahead and just rotate our slide here for a second, you'll notice that we have these two different rotations and all of these different heat maps that are going to be relating to the different parameters that you're looking at from a manufacturing perspective. So what you can see here is the X rotation and the Z rotation, which are going to be our X and Z vectors. So at different orientations, you're going to have, different support volumes required, different build times, distortion tendencies. What you can do with this is go ahead and prioritize these. You can figure out exactly what's more important for you. Maybe you want a quick build time, support volume's not that much of an issue. So this is a really great opportunity for you to squeeze Jello on the manufacturing side as well. So in addition to, doing some of the orientation stuff, we have the opportunity to go ahead and create our own supports here as well. On the left is going to be one that we did for this webinar today that VELO is going to speak about here shortly. But on the right, this is just demonstrating one of our cool supports that we can do. This is something a little bit more organic and ornate. This one's actually called the Tree of Life support. So it's a pretty aptly named application here. So the last piece here before I go ahead and transfer it over to my friend Ben is we want to go ahead and take a look at this from the additive manufacturing print perspective. And so the way we set this up is we wanted to go ahead and not do any supports on any of the internal veins. As I mentioned before, this is traditionally something that is very, very frowned upon in the additive manufacturing worlds, especially in powder bed fusion when you're just using a general machine. So what we have here are just some basic properties with respect to the manufacturing process. These don't have anything to do with the secret sauce VELO is going to talk about here shortly, but it just shows how a traditional additive manufacturing process would work with a part like this. So as you can see here on the left, we're looking at our build distortion. And so without those internal supports, you can see we're getting a large amount of distortion as we build these veins. We're going to get some geometry on the back end as we produce this part that isn't going to be representative of the part that we designed. So that's the full puzzle here is we're trying to make sure that, the part that you simulate is the one that comes out as you manufacture it. And so the last two pieces here are our von Mises stress. So basically this can signify whether you need to do some stress relief, whether you do hipping or some other manufacturing method for stress relief. And this last one here is just assuming that if we use a generic metal printer here, this is highlighting that there is a very high likelihood that we're going to have some hard blade crash severity here. So it just highlights all the areas where we might get some issues with a powder bed manufacturing. But that's why we brought our friends at VELO along. They have some amazing technology here today that can help you avoid all of these classical hurdles with additive manufacturing. Ben, would you like to take it away to show us all what you have on the VELO side?
Yeah, thanks, Ethan. Yeah, so I'll start out by going into an overview of VELO as a company. It's relatively new, started in 2014. What we've done is developed a revolutionary end-to-end process of metal additive that allows designers to print highly complex geometries without the restrictions of traditional additive. We typically deal with high-value parts in things like rockets and other aerospace applications, but also in land-based applications such as oil and gas. We've put a lot of emphasis on the ability to produce these parts repeatably on any Sapphire printer across the fleet and provide quality assurance that's really unmatched by other systems. And one final thing to take away from this slide is that all of our products, both hardware and software, are made in the US at our headquarters in California. So that's pretty unique to the additive space right now. And then going into a high-level overview of the type of metal additive we're talking about here, laser powder bed fusion. This is a really common type of metal additive, mostly because of its ability to produce high-quality parts. It's a layer-by-layer process. The way it works is there's a build plate that's riding on a piston. The piston drops down a small increment, and then a recoder comes through and distributes a thin layer of powder over that build plate. And then a laser fuses material of the cross section of your part at that given layer. After that, the build plate drops down again, and it keeps going through this cycle over and over until it's welded up the entire geometry of your part. So for traditional 3D printing, supports are common as a a necessary evil to make some geometries printable. We're welding metal, so we're introducing a lot of heat into the part, and then that material, it's going to cool and contract. If you have substrate underneath your current layer, the heat has somewhere to go, and there's enough structure to prevent any severe warpage due to that cooling and contracting. But in the case of like an overhang, like shown here, there isn't really much substrate underneath. So in a minor case, you'll end up with a really rough surface underneath there. But in a more major case, what can happen is the material will warp upward, and it could just not meet dimensions, or it could even warp upward so much that for a traditional additive system, your recoder could crash into it. So really, the supports are added to act somewhat as heat sinks, but more so as tie downs, really to prevent the material from being pulled upward by stresses. Another thing with metal supports is that they have to be forcibly removed with tools like pliers and hammers and chisels manually, which is a pain in itself, but supports really become a limiting factor when they're required in areas that you can't reach with tooling. So that's important to note going forward. So some of the key design aspects that we need to pay attention to when modifying this part for manufacturability was we wanted to maintain the design intent. So first, we wanted to keep the baffle angles at the 20-degree angles that they are. Second, we wanted to maintain unimpeded fluid flow. That means we can't have any added features in the flow paths, like any sort of solid supports or anything permanent, or even just have, we don't want to have any excessively rough surfaces that could affect the performance either. And then lastly, just to be able to mate up properly with other components in the assembly and not have any strange flow characteristics, we wanted to maintain any of the inlet and outlet boss shapes to keep them as circular. So with traditional 3D printing, there's a typical rule of thumb out there that you need to support everything below 45 degrees. It's known as the 45-degree rule. Realistically, you can sometimes push this limit down to maybe 40 degrees or so, depending on the geometry and the alloy. But on this slide, what we're showing is where supports would be added to this static mixer if we were only supporting up to that 40 degrees. On the external features of the part shown on the left, these supports require someone to break them off manually, which isn't usually very fun. If you've experienced it before, it can be a very painful process. But really, in a traditional additive shop right now, this can be someone's full-time job, removing supports like this. It can be a big time killer. But on the right is where we really run into showstopper issues. Ethan mentioned this earlier. We'd end up with supports all throughout the internals of this part, which means you can't reach those with any sort of tooling. What this would mean is that you'd have to go back to the part designer and really you'd have to ask them to make some major modifications to the part, like maybe changing the baffles from 20 degrees up to 45 degrees, or allowing us to change the shapes of the inlets and outlets to maybe more like a diamond shape or a teardrop shape that are pretty common to revert to for traditional additive systems to make them easy to print. But those changes would likely affect the intent and the performance of the part. And maybe you might be able to get clever with this and chop the part up into multiple pieces and print them all individually to deal with the support issue. But then you'd have to post-process all of these individual pieces and then assemble them later, and maybe braze them or assemble them however is needed. But really, that really just defeats a lot of the purpose and a lot of the benefits of additive manufacturing. So fortunately, with our system, we were able to avoid a lot of the headaches with supports. The baffles, they can be printed at their current angle without any issue. None of the internal geometry needed support. And then only minor modifications were made to the exterior of the part, and I'll go into those in a little bit. I did add 2 supports on these bosses on the sides, just because they're fairly beefy masses to be cantilevered out over the powder bed. But realistically, those 2 supports are just a quick break with some pliers, so they're pretty inconsequential. So this is what the final result of the print looked like. The baffles turned out really nicely. Looking at those, you can expect a surface finish on an underside like that at 20 degrees to be in the ballpark of about 12 microns SA. You can also see the quality of the inlet passage over here at the circular passage. Traditionally, a hole this size, it's about 10 millimeters. It would need to be modified to be printable, or it would need to be supported on the inside. Otherwise, it'll become extremely rough, or maybe just non-circular, or in the worst case, it could just crash your print job. On the other hand, our software, it adapts to geometries like this by applying our low angle process to produce a circular hole, and with a surface finish that we can be satisfied with as printed. So going into what enables us to print a part like that, it's really the product of the end-to-end solution that VELO offers. By end-to-end, what I mean is our system runs from pre-print setup through printing, and then through process control and quality assurance for the printing process. A user starts in our pre-print software flow. In flow, you lay out your builds and you initiate the slicing, which is where laser parameters and laser paths are generated. From that, you get a VELO print file. This VELO print file can be run on any Sapphire printer across the fleet, as long as it's set up with the same material. And while it's printing, we have our quality assurance software, Assure, and it allows you to thoroughly monitor your build in real time, but also at the end of a build, it can provide a quality assurance document that can be really useful for showing that your parts were produced the same way from print to print. Assure, the accessibility and the thoroughness of the reports is something that I found to be much more practical and manageable, and really just overall useful compared to what other systems are offering. So looking at the design changes we made to the model, first on the exterior of the part, there were some minor changes that were made. On the bases of the inlet and outlet bosses, some stock was added to make things a little more printable, where machining would be happening regardless, or where it just didn't matter. Similar stock was added on several of the external features. You can see that it's kind of triclops looking guy. We made some changes there. And then on the upper flange of the part, this was going to be machined anyway. So we increased the angle of the cone on the flange to 35 degrees, just to make sure we printed a really nice surface. Outward going cones are particularly difficult geometries to print, basically because they're unconstrained surfaces all the way around. I have another slide where I'll get into what I mean by that. Internally on the part, the only modification that was made was that we added a fillet on the underside edges of the baffles to help the as printed edge quality. But to summarize, the design intent wasn't affected by any of these changes. So when I bring the finalized CAD model into flow, it's able to recognize the features on the part automatically, and then apply specialized scan strategies to really make these features sometimes just possible, but also high quality and with a focus on high throughput. I have a few different regions pointed out here where flow would tailor the laser behavior a little differently. In bulk sections, I'm just going to focus a lot on throughput by taking advantage of our 1 kilowatt laser and how much energy it can deposit quickly. In areas like vertical walls, and specifically thin vertical walls, it can be a little more delicate to manage the effects that could be from overheating otherwise. And then on low angle, like surfaces like the baffles and for the flow channel closures, it would apply our low angle process to make sure the integrity of the downskins are maintained. By being smart enough to adapt to the specific parts geometry, it really does open doors to designs that would not typically be feasible with traditional additive. So here's a picture of the baffles, but just want to ask you, have you asked yourselves, from looking at this, would you think that this is an upward facing surface, a top skin, or a downward facing surface? This is actually a picture of the downskins of the baffles. Typically in metal additive, if you have downskins, they can be excessively rough from breakdowns, or they might have support contact points that need to be ground away to end up with a decent surface finish later. So just to expand on that, here's a different part. that shows just how low we can go and maintain a high quality surface. The part's being held here on edge on the left to give you a sense of scale. But between the veins on the image on the right, we're looking at downskins that are actually built at 3 degrees. That's obviously quite a bit below the threshold of the 45-degree rule, and we're still able to produce an as-printed surface finish of around 15 microns SA on that surface. On traditional metal 3D printers, typically I wouldn't say the surface would even be possible to print without maybe some creative support structures. And then even then you'd have artifacts you'd need to get rid of where the support's attached. So clearly our system can get away with a lot in terms of the angle extremes it can go to without support, but we do have some guidelines that we follow to avoid breakdowns on the surface. As I mentioned a bit ago, an outward growing cone is basically an unconstrained surface. And what I mean by constrained and unconstrained surfaces is that a constrained surface just has some nearby geometry that helps combat the stresses that would otherwise want to pull the part upward. These graphs on the right show just some general tendencies of how likely a surface is to break down in relation to the angle of the surface and how far that surface is building. Lower angles building for further distances are a bit riskier, but the exact circumstances of the part can make a difference on this as well. So just quickly scanning through a preview of the build and what the process would look like. So I'm going to drag through here. First, you can see the baffles starting to print. There's no support underneath the baffles. And then on the inlet over on the right-hand side, you can see there's no support in there either. This outer cavity here, something that's nice about having the inlets not supported is that when this cavity fills with powder during the process, you're going to need to drain that out after the build. So if there was support inside of this inlet and outlet bosses, it'd be obstructed, so you wouldn't be able to get the powder out very well. So having that free really helps a lot. As we go further up in the build, there are these ribs that come off the side of the part. Those build out at 30 degrees as well, without any issue. And then after it gets past the last bosses, it's pretty much home free from there. Then we have a video of what the actual build looks like from our height mapper images. On the outside of the main body of the parts at the beginning, there were 2 supports that we're building, but everywhere else you can watch and see that nothing has support building up to it. This does have this flickering effect you can see, but this is just due to the way the light is hitting the hatch patterns. The pattern of the hatching rotates each layer just to help with evening out the heating for the build. So talking about the Sapphire Printer itself for a second, the build plate is 315 millimeters in diameter. It's a circle, and the full range height is about 400 millimeters. We have 2 1-kilowatt lasers, each of which can scan the entire build plate. And we do run these lasers at their full potential to maximize throughput. I have a list later of the materials we can currently print. But for all of them, we print with 50 micron layers in an argon purged environment. And then lastly here, so the recoder, it's a really critical piece of the machine design, but I'll go more into detail on that on this next slide. So in addition to our software's ability to tailor the printing process for a given part, another piece that makes the support-free printing possible is the Recoder Design. Traditional metal additive machines use blades of some sort that physically contact the top of the part when they push powder across every layer. This isn't always an issue, but when you have delicate geometries or geometries that you don't want to disturb during the build, having a recoder come through and whack your part every layer can really make or break a print. In some situations, you may even have just part material that's just barely sticking up above the powder bed, and naturally it might have solved itself. But as soon as you hit it with a metal blade, it's game over. Your print's crashed. there are also, polymer and brush blades out there that are a little more forgiving, just because instead of crashing, the blade material flexes or erodes away a bit instead of your part. But even with that, if you get a build that survives, you've got to answer the question of whether that blade material is now embedded in the material of your part instead. The Sapphire, on the other hand, it maintains a large gap above the top of the part. It'll never touch it. So the way our recoder works is it first travels to the front of the machine and drops a very thick layer of powder across the build. And then it starts to travel back toward the rear, and there's a normalizing blade, which is still relatively high above the part. It just smooths out the top of that thick layer. Then we have a proprietary powder removal process that comes in after that and just removes the right amount of powder to get the powder bed to the desired depth. So in the event that a build is having problems and for whatever reason wants to protrude above the powder bed, we have our height mapper that takes pictures every layer and analyzes them before and after lasing. If it sees a protrusion that is tall enough to be concerning, it will start by flagging it as a warning in Assure. But if it gets to the point where it sees it as a clear risk of lifting up high enough for the recoder to hit it, it'll pause the build automatically to avoid damaging the machine. So these actual images and then the color maps, they're all kept in Assure. So it's really nice to be able to go back and scroll through them and either just make cool videos like we had a little bit ago, or to troubleshoot what may have happened during your build to cause the issue so you can correct it and move forward. So I've talked a lot about enabling parts that are complex, but size is also something to be taken into consideration. As I mentioned before, our standard Sapphire is a 315 millimeter build plate with 400 millimeter Z height. But then we also have our Sapphire MZ that extends that build height up to 1 meter if you have extremely tall parts. And then coming next year is our XC, which is a 600 millimeter build plate and 550 millimeter height. I'm personally looking forward to this system because I've had plenty of questions in the past about printing parts this size. And the answer's always been no, but it'll be really cool to enable that. And then not only for large parts either, but for significantly larger batch quantities for smaller parts too, to help drive down your per part cost. And then in addition to enabling geometries that would otherwise be difficult or impossible in some cases, we're also enabling parts to be made by bringing much more flexibility to a customer's supply chain. So something you get when working with VELO is access to our network of contract manufacturers. So to be flexible with timelines or specific capabilities, your print files can be distributed to any of our contract manufacturers. And since your print file behaves exactly the same on any Sapphire printer, any of these manufacturers can run your print file and then provide a quality assurance report from Assure to give you some comfort that it was printed the same way. Then just really quick, so we're constantly working on qualifying more materials as we go based on industry needs. The top here shows our current qualified material selection. We have a lot of the common materials, the Inconels, Ti64, F357, a couple Hastelloys, and a Scalmalloy. But we also have some more coming soon in the near future as well. So with that, I'll finish out, and thanks a lot for listening in, and we'll go ahead and jump into Q&A.
Great, thanks, Ben. Thanks, Ethan. So we do have a couple questions. I wanted to jump on the first two here, let you guys get a chance to get some water, catch your breath. Great presentations. So there was a question of whether or not we had contacts in Mexico to reach out. So I guess I'd answer with it'll really depend on what you want. If you just want a part, we actually have facilities with our printers in Texas and Oklahoma that would be able to service. If you're looking to get a hold of one of these printers, obviously you registered, so we have your contact information. If you could just let me know that it's okay to reach out and contact you, I'll have somebody do that, and then we can have that discussion. But so if you are looking for parts, that CM network is available to you if you're looking for a printer. Just give me the okay and we'll reach out to you. So the second question that we usually get, kind of preemptively get in front of it, is we do record these sessions and we will make them available at the end. It'll take about 24 to 48 hours to send you an email with the recording. The email will have a direct link to the recording and it's on YouTube. So those are usually the first two questions that we get. And then I kind of want to dive into a couple here. Ethan, on the Ansys side, there's a question from Justin. Hey, Justin, good to hear from you. Is surface roughness considered in the modeling regarding turbulence and effects like that? And if so, with what parameters and why were those parameters chosen?
Yeah, so in regard to the explore mode, keep in mind that that one is really geared for a design exploration standpoint. So the short answer to that one is that we are not considering the surface roughness. And the reason is it requires higher level discretization, a little bit more complexity from the physics perspective. So what we've done here in Discovery is allow it just to be basically a standard no slip wall condition where you're not considering the surface roughness. But what you can do directly from Discovery is transfer this directly to our Fluent product. All your boundary conditions, your mesh, your materials, your geometry, you can bottle that up, send it directly to Fluent, where you can simply just turn on your surface roughness.
Hey, Ben, you got your essay question. So somebody did ask on the downscan and Recoder Design, you mentioned that the surface roughness was quoted in essay. Somebody was wondering what essay was. We knew we'd get this one. Actually, yeah. Justin, we should put Justin on and let him answer this one. He's a surface finish expert.
Yeah, so we typically measure in essay internally. The exact reasons behind that, we'd have to dig more with our process side, but there's debate out there whether people want to measure in SA versus RA. Basically, the difference is RA is basically a linear measurement, and SA takes more of an area measurement of surface roughness. So it's a little bit more encompassing, I think, is what the idea behind using SA is. But more of the details, I'd want to reach out to our process team if there's really specific details on that you'd like to know.
Okay.
Michael,
there were a couple. Yes.
May I make a comment? This is Sunil.
Hi, Sunil. Thank you for joining us.
Sure. The one comment I also make is beyond fluid applications, remember this is a standard additive technology and it can be used for many different applications. You mentioned, what you brought to the question is really important from additive perspective. And beyond fluid, even say you're printing antennas or waveguides, that is also an area where these things become important. And we do have in Ansys tools ways to address it in electromagnetics, for instance.
Okay, very cool. There were a couple of questions that we kind of answered direct one-on-one. I wanted to bring them up in case other people had similar questions, which is sometimes the case. So there's a question here, Ethan, probably for you. Can or how does Discovery deal with fluidics mixtures? I'm not sure if I'm pronouncing that right. Or what are air mixtures? So I'll kind of let you cover that one.
Yeah, no problem. So the short answer here is that we are single phase, single species. So think water to water, no mixing of different states of matter, no liquid, no versus gaseous. So what we're doing in this example is, we purely worked with just a single species. We are going to be working on other mixing stuff. It's a little bit further down the line. It's definitely on our development timeline. It just needs a little bit more massaging in the background, but it's definitely something of high interest from our development team. So stay tuned.
Cool. And there was one more here. Does the CFD calculation work based on AI?
Yeah, so it does not. The speed of this Explore mode solver is that the solve is exclusively dedicated to the graphics card, and you need to run on an NVIDIA graphics card. So what we're doing is, if you think about kind of basics of computer science, your processor is able to answer very complex questions. You only have maybe 4, 6, 8 on your computer. But with a graphics card, this is where we're solving in the Explore mode. You have thousands of cores available. And so what we're doing is we're solving problems massively in parallel. And so, even though it may look like we're taking some shortcuts in the background, it's still a traditional solver. We are just, solving things massively in parallel there.
A couple questions kind of on market questions. It's from Denny here. So we've seen a lot of evidence in AM for rocket designs. And Ben, maybe you could speak to some of this. Have you seen AM being used in, let's say, automotive industry? Have we gotten to that scale yet?
We do have some parts that we've been doing for automotive. I haven't personally been doing that, but I do know some of our applications engineers have been working on some automotive parts. It's a little bit less of the market that I'd say is normal, just because the volumes typically, and there's not usually as much complexity. But of course, there could be certain parts that break that rule. So
there's one more question here, kind of the same person. In regards to material fatigue, is there any data that's being developed around material fatigue, and how's that being studied?
Yeah, there's actually a lot going on with that. In my previous roles and currently at VELO, that's something that's being looked at. Exact data on that and the exact progress of that, yeah, I'd have to coordinate with the process team on where that is, but that's definitely something that's constantly being looked at. That's a big thing that's looked at in additive right now.
Cool. One more question here. Do we have the capability to print multi-material with VELO3D?
No, not in the same build. Because it is a powder bed process, you'd have to have some way of blending your powders nicely in the build. That's not something that's made its way to laser powder bed fusion yet.
Okay, very cool. Well, we're about up on time, and actually we kind of ran through our questions here. I did want to have a little bit of time for closing thoughts, and maybe Ethan, a couple closing thoughts, and then how can people get in touch with you? What's the best way to do that?
Yeah, so I'll let Kurt handle the contact information, since I'm just a lowly engineer. But one of the things that I'd like to highlight here is not only in your design process, you can be focusing on the performance of the product. Today, one of the big things that we've talked about is making sure things are going to hold true on the back end as well. Discovery is a really great platform for looking at the design of a product, but it's super important to work with great manufacturing partners like VELO here today, and one thing Sunil mentioned is that if you see something here today, or if I said something wasn't available in our Discovery product, please feel free to reach out to us at whenever contact information Kurt provides. We have a multitude of products that I guarantee that we can answer your applications questions.
All right, Ben, do you have any closing thoughts?
Just that, yeah, if you have any specific questions for me, you can reach out to me directly at ben.wilson@velo3d.com. I'll also be at Rapid if you have questions and you want to talk to me there in person. I love talking about additive, so yeah, feel free to reach out.
Actually, that's a great point. Velo3D will be at Rapid. We will have this part at Rapid. So if you're interested in actually getting your hands on this part and taking a closer look at it, we'll be bringing it to the show with us. So if you are curious and want to learn more about it, please come by and check it out. And Kurt, I'll let you close out if you have that contact information that Ethan volunteered you for.
Yep, we could put it in the chat.
All right, excellent. All right, well, I think that's about all we got today. And yep, right on time. All right, thank you everybody for joining us. Have a great rest of your week, and please stay safe. Please stay healthy.